Today I want to talk about seemingly weird topic of constraint satisfaction on high-dimensional expanders. But actually, I mean, as we'll see, this is related to a lot of other things, and this is mostly something which will allow me to kind of introduce some nice concepts which may be useful in the workshop next week, and also some nice techniques. And all the while, I mean, I'll kind of mention the connections that we go into, and this will kind of keep us tethered to one concrete problem while we explore some of these concepts. Okay. But before we kind of start, let's just maybe see what is constraint satisfaction problem, and then sort of what does it mean that it's a constraint satisfaction problem, or sometimes called a CSP on an HDX. So, okay. So a constraint satisfaction problem, I mean, for this talk, some of what I'll say will generalize, but for this talk, let's just stick to the following kind of problems. So we have linear equations mod 2. Things I've written are linear equations in 3 variables. We'll mostly be concerned with this, but we'll also talk about more variables, but more or less actually. But let's say linear equations mod 2 is our model for constraint satisfaction problem for today. And we are given a bunch of equations in, let's say, n variables. And the goal is to, let's say, m equations, n variables, and the goal is to satisfy as many as possible. Yep. And by satisfy, I mean like choose values for the variables so that, well, the left-hand side equals the right-hand side for as many equations as possible. Okay. Definition okay for everybody? All right. So now, what does it mean for a CSP to be on an HDX? So let's maybe draw an HDX, and I'm going to draw a partite one, but you could don't have to. And so let's say we have some complex in which we have a bunch of triangles. Something, right? So you know what a triangle kind of stands for, and just hyperedge with 3 things, one in each part of it. Okay. Now, what does it mean that if we have such a complex that we have a CSP on this complex? Okay. And I'm actually going to ask you, so maybe, yeah, can you suggest what might be a good definition to sort of say that this CSP lives on this HDX? Okay, can you be more specific? How? Okay. Okay, good. So here is a definition, which is that you think of these variables as, sorry. And then, yeah, so the equation can be thought of as corresponding to the triangle. I'm writing a bit small, but we know what the equation is. Okay. Any other definitions? Yeah. Uh-huh. Okay, yeah. So we can have a variable for every triangle. And you could look at something like this, and then and something, right? But here, okay, I mean, these will have more than 3 equations, depends on the degree of the hypergraph, but yeah, that's fine. Any other definitions? This is like those lateral thinking, yeah. Okay, great. So you could have variables on edges, and you can have and then same equation kind of one. Okay, it's great when other people do my job for me. So all of these are kind of interesting notions of constraint satisfaction problems. And we'll talk about these two today. This one also comes up when you kind of think of Tanner codes corresponding to it. These are just hyper edges, right? We saw bits on edges in Sipser-Spillman, and then for every vertex you had a parity check. It's a parity check, right? So this kind of thing comes up when you look at Tanner codes, but I won't talk about it today. I'll talk about the first two notions. Okay. And that also means I'll just stick to three variables at least for a lot of the discussion. Okay. Excellent. And it turns out both of these are interesting and kind of behave very differently. And then sort of I'll mention some of the connections before we jump in. So it turns out this kind of problems are easy in the sense that we can get a good approximation for them. Okay. So, and they turn out to be related to coding theories. So in particular, kind of some variation of this we'll see can be used to decode Amnon's epsilon balance code that Swastik mentioned yesterday. So we'll see how to develop an algorithm for that using roughly this model of CSPs in our mind. I mean, we don't have to go through it this way, but it kind of gives a nice way of looking at it. And also it will allow us to introduce some tools which are more general and more useful. So we'll talk about it. Yeah. Sorry, I'll mention. Okay, yeah. So for now, there is no connection of BI to the HDX, but we'll come to it. So we may need to choose it. These kind of problems turn out to be hard. And what do I mean by hard? Hard, at least for some algorithms. Like semi-definite programs and so on. It actually has allows us kind of some interesting notions which are related to local testability. And yeah, and so it's also related to codes and maybe some things related to chain complexes. So okay, so we'll talk about both of these definitions. Let me see if I should mention anything else. Yeah, and these help us get some sort of explicit lower bounds because they are kind of hard instances. And then we'll see. And so the plan is roughly in the first half, I'll talk about this kind of model, talk about algorithms, and the second half, I'll talk about lower bounds and this kind of CSPs and the relevant connections. Okay. And yeah, we'll see more as we go along. Any questions before we proceed? All right. So let me erase this one. I'll keep this one for now, and I'll come back to this model after the break. Okay, so before we jump into kind of solving this problem, let's see why it's useful to decoding codes or why it comes up. And it's related to what are called direct sum codes. Max talked about a slight variation of it, but let me kind of also draw basically the same picture and label it differently. So let's think of a complex where we have kind of the subsets of size k, and let's say we have subsets of size 1. Okay. And then there's stuff in between, but I'll just focus on these two for now. And let's say we start with something where, let's say we have n vertices, and let's say we have kind of put some code here in some starting base code C0. Okay. It's and let's think of it as a block length n code. And every face kind of has k vertices, and what we are going to do is just write down the parity of those bits. And this will be a new code. So we'll just call, so this will give us some collection of bits in F2 to the whatever is the size of xk, and we'll just call that our new code. And so Max talked about a construction where you don't write down the parity, you just write all the bits. So you write down something which is like a symbol of size 2 to the k. This is just a symbol of size 2 still, but yeah, I mean, there are more of them. And direct product can be used to take a code, amplify its distance, or make a better code out of it. This one also has a similar behavior. It kind of helps us start from a base code, get a better code. But it preserves the alphabet size. So we want binary codes with really good distance, and then this is a good way of doing it. Okay. And in particular, you already saw some examples of it yesterday. So Swastik talked about the Rosenman-Wigderson construction, which you can think of as this is just subsets of size 2, edges of an expander graph. You just add things on the vertices and write them on the edge. Okay. And this we saw already improves things a bit. And now, so Amnon's optimal or sort of near optimal epsilon balance code construction that Swastik mentioned yesterday can be viewed in this way. I mean, these are not necessarily HDXs in the local spectral expansion sense, but there are some complexes, and I'll sort of only access them through some weak properties without really getting into exactly how to define them. Okay, but it has a similar flavor. And the algorithms we'll see kind of apply to all of these and perhaps more generally. All right, so that's the direct sum code. Now let's see why decoding this is kind of related to CSPs or why CSPs come up. Any questions about the definition? Okay. So the connection to CSPs, I mean, so there was one paper which looked at HDXs and direct product codes, and this was a result of Dinur. Okay, let me make sure I don't forget any authors. Right. So Irit, Dinur, Prahladh, Tali Kaufman, Inmal Livni Navon, and Amnon. Which kind of related direct product codes to CSPs through what kind of things Max was saying, maybe agreement testing, and then agreement testing is like a CSP on two things. You want to kind of make sure that what this set is telling you is consistent with what some other set is telling you. We'll take a slightly different route, and this appears in some joint works with many co-authors, and I'll mention the names again so that I don't forget them. So. Okay. So, and the connection is very natural. So, I mean, it'll take me shorter to write down than the citations. But so we are, and let's just give a name to what we did here. So this is some vector. Let's just give it a name. Let's just call it the direct sum of this little x, which was the starting point. The direct sum with respect to a complex will not always write the complex. It will just keep it fixed to the application. Okay, and so now what is decoding? So you have this code, and you transmit it, and you get a y which is possibly corrupted. And what is our job? Our job is to find some code word which agrees with y as much as possible. And what does it mean to agree with y? Well, so the goal is to find x such that So Y is corrupted, so it might not be perfectly possible, like possible to perfectly satisfy these, but we have to find the X which satisfies most of them. Okay. There is a catch, which is you have to find X in this base code C0, not an arbitrary X. Right? So it's almost like a CSP, there is this slight catch. So let's fix that. Any questions? So this is just what we said. It's the goal is to satisfy as many linear equations as possible. Okay. So now, I'm sorry. Yeah, let's take it as a linear code for now, though it's strictly speaking not necessary. Actually, wait, no. Let's take it as a linear code. I need it. Okay, sorry. Yeah, that's true. So the thing is, there are two kinds of parity constraints. The kind of constraints I get in the direct sum are actually, if you think of the code, it go in the generator matrix. The kind of constraints you use for parity checks, they go in the parity check matrix. And there I can't really mess up, like I have to satisfy everything. So I will not count them. And we'll kind of treat C0 sort of modularly. And in fact, I'll just kind of get rid of it in 2 minutes. And so we'll not worry about it. Okay. But yeah, let's take it to be a linear code. That will make my life simple. Actually, maybe I need it, but okay, let's keep it as a linear code. Yeah, I need it. Okay, so what do these direct sum constructions do? Right. So they, as we saw yesterday, they kind of reduce the bias of a code word, or kind of increase the distance, let's say, of two code words. So if I have X and X prime in the base code word, then I can think of the let's say the distance is some delta 0/2, which means that the bias of X plus X prime, and this is where I actually need linearity, is greater than equal, let's say equal to, and this balance is equal to 1 minus delta naught. So bias is something, it's some constant, not great. Okay. And I want to, and what do these constructions do? They actually tell me that the bias of the direct sum is fairly small. So, and if the bias of the direct sum is small, that also means that if I look at the distance of, so direct sum is also a linear operation. So I can look at this as a direct sum of X plus the direct sum of X prime. And that just means that their distance right, is greater than equal to half minus epsilon over 2. I mean, doesn't matter. Sort of constant factors in epsilon, I wouldn't care about. Yeah. Oh, sorry. So the bias is, okay, first of all, maybe you already noticed, but I'm writing the fractions between 0 and 1, so I'm talking about relative distance and so on. And bias is just the expected number of ones versus minus 1. So maybe more concretely, so let me just write down. Bias of X is equal to expectation over a random bit minus 1 to the xi. And let's actually take the absolute value. So, I mean, if something is kind of unbalanced, it has more ones than minus ones, okay? Then that means it also, when I write it in terms of 0, 1, it has large distance from 0, right? Because it has a lot of ones. I'm sorry? Yeah, it's expectations. I'm kind of thinking of numbers between 0 and 1 because I'll forget what is the dimension of each of these codes pretty quickly. So I'll just want to think of numbers. Okay. Now, does the statement make sense, at least? Questions? Okay. There's one important property. All of these constructions do this not only for code words X, which are in some base code, but for all X prime. You don't need to start. You just need to know that you have some distance. And then you get very large distance. Okay. being in a code is a good way of getting some distance, right? But you don't need it. You just need distance. Like, you don't need other properties of the code other than that gives you distance. Okay. And this gives us a nice way of decoding. So suppose I'm decoding to kind of half the minimum radius. So I was given y, and there is a true x, and let's say it's in the unique decoding ball. So uh, uh, whatever is the half of that. So but I find some x prime. So I find some x prime which is within the same ball. So it satisfies good number of constraints, but it's not in the base code. So this x is in C0, but I found x prime. The same. Okay. Then by triangle inequality, I know that x and x prime are not too far from each other. Yeah, so here this also works if it's greater than. If the distance is large, you get even larger. Okay. And this means that the bias is smaller. Okay. Oh, sorry. And by contrapositive, now I get that whatever I said. And always keeping my inequalities with equality. And yeah, so I don't need strict ones. Okay, is that okay? So if let's say I have some base code where I know how to unique decode, that's all I need. So you can take the Sipser-Spielman code, for example. Then I can forget about the base code. I can just try to find some x prime which satisfies the right number of constraints. And then I'll unique decode that x prime. It has to be close to my starting x. Okay. So then I have a pure CSP. I'll just drop this condition. I'll just call this x. I'm not going to write primes all the time. But now we just need to satisfy as many constraints as possible. Everything else is just taken care of. At the end, what we get, we will just unique decode it in the code C0 and find the closest code word. Everyone okay so far? Okay, good. So now it suffices to solve CSPs on maybe these kind of complexes, maybe high dimensional expanders and so on. But let's first solve CSPs on low dimensional expanders. Let's see how to do it, and then we'll kind of come back to this picture. In fact, that's where most of the ideas will be. So now I'll just think of two variables per equation and something even simpler. Okay. Mm. See. Okay, so now let's think of kind of expanders we like. Let's think of an n-vertex deregular graph. And let's think of it being lambda regular, sort of a lambda expander, where I'm thinking of the normalized adjacency matrix. So okay, so this is going to be our setup for the next few minutes. And right. And now we have equations on the edges. Yeah, let's say some bit. Is the model okay? The goal is still the same, satisfy as many as possible. Yeah. No. Excellent. Okay, good. So it can happen here. But the kind of easiness I'm talking about is actually finding very good approximations. And TOSAT, it's easy to check if it's perfectly satisfiable. But if I give you something which is kind of close to satisfiable or where it's not perfectly satisfiable, but your goal is to find as many as possible, then it's not always easy to approximate. You can approximate it within a constant factor, but you lose some factor. Here we'll try to do better. So if it's possible to satisfy 90%, I'm going to give you something which satisfies 89.99%. Okay? This sort of task is not easy even for TOSAT. Okay? That's a very good point. Other questions? Yeah, please catch me. I might sweep something under that, but yeah, that's a good point to catch me. Okay. So now, okay, I'm going to work with expanders. Kind of, I like functions, so let me write down some functions and then just kind of phrase the same problem in terms of functions. Okay. So from x, we are going to create a function where f sub of xu is equal to a plus minus one value depending on the value of x. From we were calling this y. Okay, let me stick with that. Sorry, that's what we called it there. Okay, and from y, I'm going to create a function g, which is on the edges. And I'm also going to, okay, so now the goal is to find the maximum, find an x or find an f which agrees with g as much as possible. And what does agreement mean? So the goal is to but this notation is just saying G has two inputs, F has one, so it's kind of not a fair comparison. And this is just a function where we think of, okay. Just the product. Okay. So it's like a tensor or vector-vector transpose. That's just the notation I'll use. Okay. And now the goal is to find the maximizer of this. I've kind of switched parameters a little bit. So here, this is sort of like the bias kind of calculation. I'm agreeing sort of, so if they agree, I'll get a 1 in the product. If they disagree, I'll get a -1. So I'm actually counting agreements minus disagreements. Okay. Instead of just the fraction of agreements. This will make a big difference if I was giving, let's say, a factor 0.7 approximation to agreements. That might not mean much in terms of agreement minus disagreement. Okay. But I'm going to give an arbitrarily good additive approximation. So it's fine to study this one. Okay. And then we'll just work with this quantity for now. Questions? Okay. So we'll come back to this. But here's my hidden agenda for this talk, or maybe not so hidden anymore, is that there is kind of a nice tool known as a graph regularity lemma, in particular what's called the weak regularity lemma. So it's due to Fries and Kannan from 96, and I'll give a slightly different version of it. That actually lets us study these kind of questions in a very nice way, and it can also be extended to expanders and so on. So this was originally for very dense graphs. And if there is one thing kind of I want you to take away from this lecture is just kind of what the definition is or how to apply it, or maybe a slight generalization of it. And what it does is that it kind of lets us take this G, which is possibly an arbitrary function, and build a very simple, very structured approximation for G. Okay. So it lets us build, but H is very structured, very simple. Okay. Such that is very small. So, and depending on the quality of approximation we want for all f. So even if we don't know what f we are going to apply here, this approximation is going to work for all f. So in particular, it will work for whatever might be the optimal one. But then we will switch to studying the structured approximation, and we'll see that that gives a very nice and simple algorithm. Okay. So now our goal is to develop this kind of an approximation. So let me write a slightly more abstract version, which I'll prove. And then we'll come back and kind of deduce some statements of this. Okay, so, and this is called the weak regularity lemma. Okay, by the way, it's not because the lemma is weak or this, I mean, there's also something called Samaredi's regularity lemma or the so-called strong regularity lemmas and so on. And actually there is an argument of Terry Tau which can prove those lemmas by iterating this lemma. So the lemma is not weak, it's very strong. Just the condition is known as weak regularity, this sort of approximation. In the others, you need some stronger kind of approximation, and those are called strong regularities. Okay, but the lemma is very powerful. Okay, good. So now let me give an abstract version. So and in this form, it appeared in a paper with Luca Trevisan, Salil Vadan, and myself. But I mean, there are also many other versions of regularity lemmas for expanders due to Koyaogla and Hooper and Fries and Bodwin and Mempala. So you can look up sort of weak regularity expanders, you'll find a lot of reference. Okay, but I'll just stick to one version for now. And it's the same, except I'll kind of forget a little bit about these kind of functions. So let's say G is an arbitrary function from some, let's say, finite space X to, let's even say -1, 1, the interval. It doesn't have to take exactly the boundary values. Okay. And let's say we have some inner product defined by some distribution mu on X. Okay, so like in our expanders, we kind of had these different probability distributions on different faces. So just think we have some probability measure, and we'll define inner products the same way by expectation according to this. And let's abstract out the class of functions which we want to. So we'll think of these as kind of distinguishers. They're trying to distinguish G and H, and let's try to abstract out our class of distinguishers. Okay, so let's just say F is some subclass of functions. Yeah, let's say this. Actually, I just need something weaker, so let me write something weaker. Okay, where the norm is defined again by this inner product. So take the inner product with itself, take a square root, or don't, less than 1. Okay. Now, I switched a little bit. So there we had this kind of funny F tensor F, because this F was on a different domain than this G, and so we were trying to match them. Okay, here, for now, I'm just going to think of F on the same domain just to write things cleanly. And then we'll just kind of take the F tensor F of that F to fit it here. Hopefully, that's not too confusing in terms of notation. Okay. Everybody likes F for their functions, but yeah, can't use too many. All right, so, and now there is, the lemma says that for every epsilon, which is the quality of approximation, okay, so now epsilon, think of it as a free parameter. It's not related to the bias of the code or anything. That epsilon is gone for now. We've forgotten about the code. Okay. For every epsilon, there exists an H, which is actually a linear combination of these FIs, of what FIs? FIs from this class. Okay, let me say. Real number. So, such that 3 things happen. It's a good approximation. Hmm. And it's simple. So in some sense, it doesn't use, like, it's not a very complicated approximation. And we'll capture that by saying how many things appear in this summation. I mean, like if I had a really large class and I kind of wrote some infinite summation and so on, then I could probably build all kinds of crazy function approximations, but we don't need that. All we need is that R is actually small. It's in fact constant depending on epsilon. And also the coefficients are not too large. So the sum of the coefficients is 1 over epsilon. Okay, is the statement fine? Yeah. Right, so yeah. For all G, for all measures, and for all classes of distinguishers which satisfy this, the norm is bounded. Okay. There exists and for all epsilon, there exists an H of this form which satisfies these guarantees. Yes, so then it's easy to construct H. Okay, sorry, it's less than, right? So I could just take that F or something very simple. So small distinguisher sets are easy to fool. I can build a very simple kind of approximation, but it will be interesting when F is very large. And in fact, I didn't say it's finite, so it could be infinite even. Yeah. No. G is not in the class F. I'm sorry. Right. Right. F can only be a scaling of that. Right. So, I mean, you just take the scaling. And so, first of all, you just start with your approximation. In fact, the algorithm I'll say will still work. But you start with either that one single function has inner product more than epsilon with G or less than epsilon. If it has more than epsilon, subtract it. Now the inner product will go down a little, right? And keep doing this. In fact, that's the whole algorithm even generally. Okay, but even singleton will work. The coefficients, yeah, we'll choose. You'll see the proof. Just basically, as Max said, project. But and the remaining part will be orthogonal, so you'll get 0. Yeah. No.
Suppose if P is constantly 0 and P is constantly 1.
Then we don't need to approximate because the inner product is already 0. Right? F is constantly 0. So the inner product with G is also 0. So we take H to be 0. It has the same inner product with F. Yeah. So let's see the proof and then we'll see what happens for this particular case. Okay. But no, I mean, it's good to ask questions because it's a counterintuitive statement. It's not, I mean, the proof is not complicated, but it's weird. Like you have so many quantifiers for all there, and then all of these things, you can just find some simple H which approximates everything. No, this is arbitrary. So X is an arbitrary finite set. Okay, with this measure, okay, with some measure. I'm not using anything about this measure or this. Okay, so yeah, it's a general statement and perhaps somewhat surprising when you see it for the first time. And it's actually, the proof is shorter than the statement of the theorem. So it's, and I'll kind of imitate swastik and say a 2-word proof, which is gradient descent. And maybe you know what gradient descent is, maybe you don't, but I'll give a full proof anyway. Okay, so if you know what gradient descent is, we are basically trying to minimize this following function, which is, or functional, it's a function of H. Okay, so, which is just, or max or supremum if F is infinite. We're just trying to do this. And actually, let me assume F is closed under negation. So I just kind of take the negations of all functions and include them in F so that I don't have to worry about absolute values. This will just make my life a little simpler. We'll just change F by adding all negations. Okay. But yeah, okay, let me keep this version. What is this? This is just a supremum of linear functions. It's just, right? This is a convex function. And we can minimize convex functions. And what is the optimum of this? I mean, like if I search over all H, what is the minimum value of this expression? H was not restricted. H is arbitrary. Take whatever function you want. Doesn't have to be of this form. What is the right answer? Sorry? 0. So it's 0, and what we know is gradient descent in kind of 1 over epsilon square steps gets epsilon close to the optimum. And what are the steps like? The steps are gradient. What are the gradients of this function? It's one of the f's. It's just a piecewise linear function. So at every step, gradient descent kind of takes a step in the direction of one of the f's. And after 1 over epsilon square steps, we are epsilon close. Okay. Yeah. No, I'll do the proof. I'll do the full proof. Sorry? Why is this 0? We can take h equals g. If we were just minimizing this over, right? If we're sort of if we were minimizing this, so yeah, I mean, if it's unrestricted, then the optimal is 0. Okay, good. And the proof is the following. So start with h0 equals 0, and just have this while loop. While there exists an ft which distinguishes g minus h. I'm ignoring the absolute value because I just made that assumption f is closed under negation. Otherwise, yeah, put the absolute value. It'll just require one line of case analysis in the next step. And then I'll just update it. Oh, sorry. And when the loop terminates, whatever is the final outcome. T goes to t plus 1 and so on. So I'm not writing on it. Okay, is the algorithm okay? I mean, this is the algorithm which is supposed to construct such a. I have not proved that it terminates in sort of when it terminates, we are good to go, right? Because then there doesn't exist such an f if the loop terminated. Yeah, take any, doesn't matter. Yeah, so this kind of corresponds to there are many subgradients and so on. You can pick it. Okay, good. Oh, yeah, thank you. It's a HT. Yeah. This is the one I'm constructing. Okay, and the proof is just the following. So we are just going to study how the norm of this vector looks after an update. So, I'm sorry? Yeah, which is gradient descent. Yeah, I mean, you've seen this many times before. This is nothing new, but it's kind of nice that it proves this lemma. It's and it's like once you realize how flexible this lemma is, kind of powerful. Yeah, more questions? Okay, so we are going to look at how the norm of this function changes after an update. So I'm going to write ht plus 1, but I know ht plus 1 is just ht sort of this plus this, right? So this is ht plus 1, right, by definition. Okay, and now let's open up the norm. It's kind of g minus ht minus epsilon times ft. So this term will kind of cancel out, and I'll be left with 2 times okay, everybody believes me that this. Oh, yeah, thank you. Yes. Very good. Okay. And now we're done. So we know this is greater than equal to epsilon. And we know this is less than equal to 1. So this term is at least 2 epsilon square, and we are subtracting at most epsilon square. So the norm goes down by at least epsilon square to begin at every step. Okay. And we started at 1. G was kind of had values 1 minus 1. So the expectation of square or whatever will be at most 1. So we started at norm 1. We go down by epsilon square at every step. We can't keep going. So it has to terminate in 1 over epsilon square steps. And when it does, so every time the Ci we chose was just some epsilon, right? Actually, if you kind of remove the assumption that it's closed under negation, then this could be plus or minus epsilon, depending on whether ft distinguished or minus ft distinguished, right? So it will be some coefficient with absolute value epsilon. And you can have the same ft multiple times, so they might add. But at the same time, you are adding coefficients which are all epsilon in absolute value, and there are 1 over epsilon squares of them. So this kind of proves that r is less than equal to 1 over epsilon square, and the summation, the sum of absolute values of CT is less than equal to 1 over epsilon. Okay. So that's the proof. Everyone okay? All right, so now I called this an abstract version of the Fries-Kandon regularity lemma and so on. So let's maybe go back and see why, and let's connect it to the kind of statement we had there. Okay, so now let's think of some graph. Okay, so some arbitrary graph, not necessarily our regular expander, but some arbitrary graph. Let me call it G prime. Let's say the vertex set is still n vertices. So, and we will take the function to be the indicator of edges. So, and we will take our measure mu to be just uniform on pairs of vertices. Okay. So just pick a random u, a random v independently. And we'll take our function class f to be what are called cut matrices, or just sort of products of indicators of sets. Okay, so it's just going to be 1 if u is in S and v is in T for some S and T. So S and T are arbitrary subsets. Okay. This is the setup where we are going to apply the lemma we just proved. And what does it tell us? So it will find us an H, which will look like summation Ci. Again, not too many of them, etc. And such that the inner product of, such that for any function now in this class itself, so the difference is small, right? Sort of this quantity is small in absolute value. Okay, but let's see what this quantity is. So first of all, G is this function, and if I look at its product with this function, so what is G inner product this? Let's write it down. Not necessarily, but you can start with that if that's easier. So G is a function on edges, right? So, and this is an indicator of S being in U and T being, V being in T, and this is just checking if UV is an edge. So this is actually maybe 1 over n square times the number of edges between S and T. When the number of edges, you have to define it a bit more carefully. If they overlap, then you just count it twice. Okay, good. And what is H? I mean, H is built out of stuff of this form, and it just counts the intersection, again, normalized by n square. Okay, sorry, oh, Ci, thank you. Okay, good. So that's, so it just says that there exists a small number of sets, S1, S2, so on, such that you can count the number of edges between any S and T by just counting the intersection with these sets, okay, with some linear combination. How much is the error? Now the error is epsilon n square. So the difference between these two, because sort of with this normalization of 1 over n square, the error is epsilon. Okay. When you take the n square on the other side, the error is epsilon n square between these estimates. So this lemma was originally defined for dense graphs. Okay. So when the number of edges is already some like 0.1 times n square, then epsilon n square is tiny in comparison. There are extensions of this to things which are like dense subgraphs of expanders and so on, and we'll apply it in such a setting. I mean, I could do it in two ways. Either I could kind of change this lemma a little bit and do that. I'll just kind of keep this lemma. I'll just use a better mu, and then we'll switch how to apply it to expanders. Okay, but this is the usual statement in the Fries-Kandon regularity. Any questions? Okay. Sorry?
When you define G, each edge has a sign.
Yeah, but it doesn't have to, right? I proved it for anything which has any values between -1 and 1 in the interval.
So here, EST means the weighted sum always just between.
So right now I'm thinking of G as just a 0-1 function, an indicator function, right? So weighted in the sense, yeah, if S and T overlap, then I count it twice, yeah.
This G and that G.
Yeah, they are different. I'm sorry, I'm overloading notation a little bit, but I don't have too many letters for functions. And primes and tildes only get so far. Okay. So now let's go back to the problem we were trying to solve and see why this basically solves it. Okay. Right. Excellent. So we were trying to solve this problem. For a given G, which was kind of coming from some constraint satisfaction problem, we were trying to find an F which comes from an assignment, right, which satisfies as many constraints as possible. Okay. Yeah, thank you. I mean, I might do this a few times today. I might go on tangents because my goal is to actually introduce those concepts. But yeah, please let me know if something was forgotten in the detour. Okay. Yes, I mean, if you solve this exactly, you solve this exactly. The quality of approximation, like depending on what kind of approximation. But if I give you an additive epsilon error here, it's still an additive epsilon error here in the fraction of constraints that are satisfied. But that's the kind of approximation I'll be dealing with. So yeah, when you do this translation, you have to be careful about when you do multiplicative approximations, it means something very different in the two translations, but I'm not going to talk about them. Yeah. Okay, thank you. Excellent. So this is, yeah, the uniform distribution on the edges on the d-regular expander, or what Max called pi2. Okay, good. So now, yeah, so I'm going to apply the regularity lemma. Can I erase this part? It's okay. Let's hopefully remember this translation. Okay, let me erase this. I'll keep that general statement. Okay, so now we apply the lemma. So G is what was given to us. It's a function from edges to -1, 1. I mean, it doesn't have to be -1, 1 exactly. We take a function class f to be, I'm going to take it slightly more general than what we need. So I'm going to take it as an asymmetric version of that. Okay. And the reason for that is algorithmic. So I kind of told you all this lemma, but it sort of looks like a nice algorithm, but I didn't tell you how to do this step, which is if there exists an FT, find it. This is the algorithmic challenge in this lemma. Okay? I'm assuming that we can do this. In this case, it turns out we can do this with some approximation, which is okay. But yeah, I'll not talk about that for now. Suppose we have that. And now, the lemma kind of gives us an H such that, so again, take the epsilon in the lemma to be small enough, and I can kind of look at an H which is of this form. Where these comes from this class, which is closed under negation. And I can kind of reduce to studying so I can reduce to studying this kind of a question now up to a very small or arbitrarily small epsilon error. And now let's look at this. So, I mean, I claim this is very easy to understand. Again, this is mu, which or this pi 2, which is just a uniform distribution on edges. Okay. So now let's study this term by term. And it's fi1 of u, fi2 of v, where uv is a random edge. So let's write down the full expectation. Okay. And now let's just combine these two. And let's combine these two, which are functions of v. And so when I write this, I look at expressions of the form, and let's call these two a big F1. Let's call these two a big F2. So, okay, let me not sum over CIs for now because I'll need indices for big ones. But it's just an expression of the form over UV, big F of U, big F of V. Oh, sorry, F1, F2. Okay. Does this remind you of something? Excellent. So we know that if I sampled UV independently at random, okay, which is just the product of expectations. Then this difference is small by expander mixing lemma. And what is this quantity? This is nothing but the inner product of fi1 and f, and this is the inner product of fi2 and f. Because this was really the product of those two functions, right? Expectation of the product is just what I call the inner product. Okay. So now we got the following. So we already reduced to studying h, and we got that h is a very simple function. Up to this error. Lambda, and I'll pay this cost for every term, and the sum of the absolute values of the CI is 1 over epsilon, so it's at most lambda over epsilon. Okay. Let's assume lambda is less than epsilon square. So we want a sufficiently strong expander to apply this. Okay. So then this is still less than epsilon. Okay. So now we can kind of study this expression, which is even simpler. And now I claim it's so simple that we are done. So let me mention why. So now observe that the quantity we are trying to study is approximated by just a function of these inner products. So if I have these bunch of functions f11, f12, f21, f22, so on till fr1 and fr2, then the quantity we are studying is just some linear combination of inner products of f with one of with these functions, right? So we don't need to know f on all the n points. We just need to know these 1 over epsilon square or 2 over epsilon square inner products, which are real numbers between -1 and 1. And once we know this, any f which has the same inner products, there can be many f's which will have the same inner product with these, or even close by, they will have the same value for this expression. And so they will have the same value for this expression, up to some small error. And so they will have the same value for this expression. So I can just maximize this expression and sort of find whatever f I get as a maximizer and just output that. That will be pretty close to this one. Yeah? Yeah. I'm sorry? This one? Right. So for each term, the difference is less than lambda by expander mixing lemma. Okay. And when I sum over the errors for all the terms, for each term, I'll kind of incur an error, which is the coefficient of the term times lambda. And the sum of the absolute values of the coefficient is at most 1 over epsilon by what I just erased, sorry. Okay? Good. Yeah. So we don't know. We'll get to that. Yeah. Other questions? Yeah. So I have to tell you how to search over these Fs. But yeah, so we will have to find out. But I'm at least saying that I just need to understand a few things about F, just these inner products. Okay. Yeah. Yes. Right. So this was EML, which I used to understand every term in the regularity approximation. And then because the sum of the coefficients is small, and then lambda is sufficiently small. Okay, good. I'm sorry. Can what? So these are all the functions that appear in the regularity decomposition, right? These are all the functions fi1, fi2 for I between 1 and r. Right? So these are all the functions. There are constantly many of them, 1 over epsilon square. And I just claim I need to understand the inner product of f with each of these constantly many functions. That completely controls the optimization problem. Right? Once I know those 2 over epsilon square numbers, I know everything. Right? So f was like a large function. It was like n values in plus minus 1. It was a very large space. Now I have this tiny space. Okay. How do I search over this space? Not complicated. So let's think of the partition generated by these constantly many functions. I'll call it P. So, I mean, yeah, so we don't know how to find an F which has inner product 0.1 with this, 0.2 with this, and so on and so forth. Like suppose these are just constantly many numbers, I could just guess them. And again, as I said, it's okay to guess them approximately. I can guess them up to some error of epsilon to the 4. And there is a space of size between minus 1 and 1 for each inner product. If I guess them with discretization of 1 over epsilon to the 4th, there's only a small number. So I could just try all guesses for these inner products. But I don't know if I just guess these inner products, is there a right F with all those inner products with all these functions? But there's a more refined way of guessing which does this. So let's think of the space on which F11 is 1 and the space on which F11 is minus 1. And now let's think of the space on which F21 is 1 and sort of our F12 maybe. Let's start 1 or minus 1. Okay. Now let's think of the space on which I don't know, F21 is 1 or minus 1, and so on. So like we can keep dividing this space into 2 parts based on each of these functions. It's a small list. What is the number of parts we will get? Exactly. So 2 to the power, well, 2 over epsilon square, because for each r I get 2 things. Okay, good. And now I claim if I know what is the fraction of 1s or minus 1s of f in each sort of atom of this space, then I know all the inner products. Right? Because what is the inner product? It just says how much f agrees with this one or that one. Okay? This is the partition generated by all of them. Right? So if I can write down the number of 1s or minus 1s of f in each piece of this partition, it tells me all the values of the inner products. Okay? And so now I just need to guess for each piece, just a fraction. I don't need to actually know where the 1s and minus 1 are. That's important because just the fraction determines the inner products, and any function which has the same fraction in each piece will give me exactly the same value. I don't need to distinguish them, right? I can just output any one of them. Okay, and now this is the whole algorithm. I just find this partition. On each piece, I guessed what is the number of 1s or minus 1s. And I say, let's say I guess it up to some discretization gamma. Okay, so I'm guessing, let's say, the fraction of 1s, it can be either 0 or gamma or sort of 2 gamma, all the way up to 1. And I guess this for every piece of the partition. I just enumerate over this space. This gamma is some constant depending on epsilon. I didn't calculate it exactly. Yeah. Yes. Okay. And I mean, I'm claiming that's, for our purposes, that is F. We don't need to know anything more about it. Yes. Yeah, because it just tells you agreement or disagreement with each of them, right? And these can be guessed separately, right? There is no collision between them. Like I can guess these pieces. There is no conflict, right? I mean, this doesn't impose any constraint on this part. The inner products could have imposed constraints on each other because we didn't know how these functions overlap. Okay. So I just guess all of them. and I output the best f. This gives, again, if you set the parameters right, an epsilon approximation or maybe 2 epsilon approximation to this problem, which was how many constraints can be satisfied. And epsilon can be arbitrarily small. Okay? We just need lambda to be sufficiently small compared to epsilon. Okay? This is not for free. For sufficiently strong expanders, we can do this. Okay? Okay, maybe let's take a break here, and then it's just a very, very simple step to go from here to high dimensional expanders and so on, but let's do that after the break. So, any questions before we break? Yeah, please. Yeah. Yes. Yeah. Well, okay, that's separate, but instead of G, we said find me something which is close to H. Now, H happens to be of this form. That came from regularity. So the search is still over this same kind of F tensor F. It's just that the form of H has asymmetric terms. That's just for algorithmic reasons. I mean, in principle, the regularity lemma would have built an H with the same term, but the algorithmic part would not work. So for algorithmic reasons, I can broaden the search space a little bit. That just increases the number of functions with which I need to study inner products by a factor 2. It doesn't really matter for me. And then I just enumerate over the values of all these inner products by going at this partition. Okay? That's the whole algorithm. Okay? This is for expanders. We'll kind of take it to high dimensions after the break, but not that bad. Yeah. Mm-hmm. For algorithmic reasons. So the step in the box on there, I would not know how to implement. So, yeah, I didn't tell you how to implement that algorithm. I just told you it works, right? And if you want to know sort of finding an F which is sort of maximizing a quadratic form with a matrix and over Boolean or plus minus 1 values. So it's not easy to do for symmetric quadratic forms. I mean, I can have a log n factor loss in the approximation. But if I have two different ones, then it becomes Grothendieck problem, and for which there is a constant factor approximation. So when I reduce this to the asymmetric case, I get the algorithmic part pretty easily. And that constant factor approximation just goes into this 1 over epsilon square. It becomes like 10 over epsilon square or something. Okay, yeah, I hit that part, sorry. Yeah. R is less than 1 over epsilon square. Yeah. Yeah, is at most 2 to the 2 over epsilon square. Right? For every function, I get 2 pieces. And yeah, I mean, there's also like if you know something about the VC dimension of these kind of functions, then you can get better bounds and so on. And there are versions which will do that. So like you can get a better growth. But yeah, I'm not. And also, you don't really need to do all this guessing. You can actually write a linear program or something to search over correlations. You can shave one exponent and so on. So there are many things you can do better. I'm just not doing any of them. But this is just the most naive version of this. Other questions? Okay, so let's come back after the break and see how to go to high dimensional expanders. Can we ask them not to erase some of this for now?